Here's a challenging problem from our assignment about random variables. This problem is going to involve some normal calculations and also random variable transformations. So I'm going to walk you through step by step. So this has to do with the amount of nitrogen oxides present in the exhaust of a particular type of car. It varies from car to car according to a normal distribution with a mean of 1.4 grams per mile and a standard deviation of 0.3 grams per mile. Two randomly selected cars of this type are tested. One is observed to have a 1.1 grams per mile of nitrogen oxide, and the other has 1.9 grams per mile. Important thing to notice here is that these are values of a random variable. Okay, so observations that vary according to a normal model. And we can see that one is slightly farther from the mean than the other. The mean is 1.4. The test station attendant finds this difference in emissions between the two similar cars surprising. Okay, if both cars are supposed to be the same, why are they so different? If the nitrogen oxides levels for the two randomly chosen cars of this type are independent, that's important so that we can combine variances, add variances, find the probability that the difference is at least as large as the value the attendant observed. Okay, so I think the key word to start off here with is difference. We need to find the difference in these two random variables, what we observe, and compare that to what we would expect. Okay, so our new random variable, let's just call it W like the last problem. The new random variable should be x1 minus x2, but it could also be x2 minus x1. I want to keep that in mind, right? There's no there's no instruction as to which value we should subtract from the other. So really it's just x minus x, which can happen in more than one way. Okay, let's start off by finding what would we expect the mean of W to be. What would we expect the standard deviation of W to be? So the mean of W should, intuitively, we should know that it's just 0. If the two cars are the same, in theory, if everything went according to plan, they would have the exact same emissions, and the expected difference between the two should be 0. We would expect no difference. The standard deviation of W is the standard deviation of x minus x, which is the square root of the variance of x plus the variance of x. Remember, it's really important to remember that even when we subtract random variables, we still add their variances. We get more variability in the distribution of the difference than we do in the individual observations. So 0.3 squared plus 0.3 squared gets us 0.18. Square root of that, 0.42. Okay, so now we have our new mean and our new standard deviation of this new random variable, which is defined as the difference between two randomly selected cars that come from the same distribution. Okay, here's what we expect. What did we observe? We observed that one of the cars had emissions of 1.1. The other had an emission of 1.9. So 1.1 minus 1.9 is going to give us negative 0.8. Well, what if we did it the other way around? What if it was 1.9 minus 1.1? Well, that would give us positive 0.8. And we'll see why it's important to consider both of those in a minute. Okay. Now, next piece, wow, there's a lot to this problem. They vary according to a normal distribution. That's what we're told, a normal distribution. Okay, so if each variable varies according to a normal distribution, then the combination of x minus x should also vary according to a normal distribution, with an expected difference equal to 0 and a standard deviation of 0.42. Okay, so we could write out all of our standard deviations, or we could just kind of make a guess as to where the value of the difference should fall. So here's one observation for x minus x, positive 0.8. Here's another. Negative 0.8. Okay, so the question is, what is the probability that the difference is at least as large as what we observed? Okay, so what we observed was either negative 0.8 or positive 0.8. I'm going to take both sides of my normal distribution to find that probability, the probability that the difference was at least as large as what we observed. In order to do this, I might go ahead and I might do z-scores. I might do the shortcut that we've been using recently and say, I'm going to do normal. Actually, let me be more precise. The probability that the difference is less than or equal to negative 0.8 can be found using normal CDF. I need a lower boundary, which is very, very small. I'll do 10,000. I'm not going to put commas in here because it will get confusing. 1,000 would be fine too. That's my lower limit. That's my approximation for infinity, negative 10,000. And then I have negative 0.8, comma, my mean, which is 0, my standard deviation of the difference, which is 0.42. Okay, that will get me this lower shaded area. Okay, probability that the difference x1 minus x2 is greater than or equal to positive 0.8. I might not want to do all this work again because I know because of symmetry it will be the same, but let me write it out. It's good practice. Normal CDF. This time my lower bound is the positive 0.8. My upper bound is going to be the 10,000 to approximate positive infinity. Mean is 0. Standard deviation 0.42. Okay. So the sum of these two probabilities should give me the overall probability that the observed difference is as large as 0.8 or larger in either direction, really. Negative 0.8 or positive 0.8. So let's go ahead and do that. So second bars, normal CDF. I'll start with my lower bound. It can just be any really small number. Then I'm going to plug in negative 0.8. I'm going to plug in a mean of 0, standard deviation of 0.42. I'm going to say paste, and then I'm going to get the command that I wrote on our screen, 0.028. I'm going to multiply that by 2 because I have both sides. So 0.057, if I round, should be the answer. Okay, that's my answer. The probability that the observed difference is as large as what the attendant saw, or larger.